This is a part 9 of mathematical physics. In this video we discuss about remaining part of a complex number, some basic property of complex number, argument z1 z2 equals to argument z1 plus argument z2. Here argument of z1 by z2 equals to argument z1 minus argument of z2. Here if we take mod of z1 plus z2 and their square and add with mod of z1 minus z2 mod square equals to 2 times of mod of z1 square plus mod of z2 square. Here cos theta plus iota sin theta is equals to e raised to power iota theta. Here de Moivre's theorem, if cos theta plus iota sin theta is given and whole power is n, we can write equals to cos n theta plus iota sin n theta. Now for finding roots of complex number, here cos theta plus iota sin theta we can write equals to cos 2m pi plus theta plus iota sin 2 pi m plus theta. For finding roots of complex number having power n, we take here cos theta plus iota sin theta whole power 1 by n and equals to cos 2m pi plus theta plus iota sin 2m pi plus theta whole power 1 by n. Using here de Moivre's theorem, we can write this cos 2 pi m theta divided by n plus iota sin 2m pi plus theta divided by n. Now circular function of complex number. Cos of theta equals to e raised to power iota theta plus e raised to power minus iota theta divided by 2, and similarly for sin theta e raised to power iota theta minus e raised to iota theta divided by 2i. Now for this is for if we finding cos theta and sin theta in term of complex number, cos z equals to e raised to power iz plus e raised to power minus iz divided by 2. Here sin z equals to this. Now hyperbolic function. Sin hyperbolic x is equals to e raised to power x minus e raised to power minus x divided by 2. And for cos hyperbolic, we can write this. Similarly, for tan hyperbolic, as we know, tan x is equals to sin x divided by cos x. Similarly, this property also work for tan hyperbolic x also. So we can write here tan hyperbolic x is equals to this. And similarly, cot hyperbolic x is equals to reciprocal of tan hyperbolic x. So we can write here this. And similarly for sec hyperbolic x and cos hyperbolic x, here cos hyperbolic x plus sin hyperbolic x equals to e raised to power x. And another property is cos hyperbolic x minus sin hyperbolic x equals to e raised to power minus x. Here if we apply De Moivre's theorem for hyperbolic function, it also work like as we used in cos theta plus sin iota sin theta whole power n, or we can write cos n theta. So we can write cos hyperbolic h nx plus sin hyperbolic nx. Now relation between circular and hyperbolic function. Sin iota x equals to iota sin hyperbolic x. Cos iota x equals to cos hyperbolic x. Tan iota x equals to iota tan hyperbolic x. Sin hyperbolic iota x equals to iota sin x. Cos hyperbolic iota x is equals to cos x. Tan iota x equals to hyperbolic iota x equals to iota tan x. Now some formulae for hyperbolic function which are different from trigonometry. Cos hyperbolic square x minus sin hyperbolic square x equals to 1. Sec hyperbolic square x equals to 1 minus tan hyperbolic square x. Cosec hyperbolic square x equals to cot hyperbolic square x minus 1. Cos hyperbolic x plus y plus minus y equals to cos hyperbolic x cos hyperbolic y plus minus sin hyperbolic x sin hyperbolic y. Now another tan hyperbolic x plus y equals to tan hyperbolic x plus minus tan hyperbolic y divided by 1 plus minus tan hyperbolic x tan hyperbolic y. Now cos hyperbolic 2x equals to cos hyperbolic square x plus sin hyperbolic square x, and tan hyperbolic 2x equals to 2 tan hyperbolic x divided by 1 plus tan hyperbolic square x. Now another cos hyperbolic x minus cos hyperbolic y equals to 2 sin hyperbolic x plus y divided by 2 into sin hyperbolic x minus y divided by 2. Now some important expansion. Cos n theta can be written as cos raised to power n minus nc2 cos theta, cos theta raised to power n minus 2 sin square theta plus nc4 cos raised to power n minus 4 theta sin raised to power 4 theta plus up to so on, and sin n theta is equals to nc1 cos raised to power n minus 1 theta sin theta minus nc3 cos raised to power n minus 3 sin or cos theta sin cube theta plus n raised to nc5 cos raised to power n minus 5 theta sin raised to power 5 theta up to so on. Now geometric series. If this type of series is given, this sum equals to this, and if a plus ar square up to infinity goes, so it's equals to a divided by 1 minus r. Now binomial series. For 1 plus x raised to power n, we can write here this. Up to so on. And for sin x series, we can write here divided by 3 factorial plus x raised to power 5 divided by 5 factorial minus up to infinity. And for cos x we can write here 1 minus x square divided by 2 factorial plus x raised to power 4 divided by 4 factorial minus up to infinity. Now for sin hyperbolic x, their expansion become x plus x cube divided by 3 factorial plus x raised to power 5 factorial up to infinity. Here there is no negative term as compared to sin x series. And for cos hyperbolic x, we can write here this. Similarly for cos hyperbolic, there is no negative term. And for tan inverse x, their expansion equals to this, x minus x cube divided by 3 plus x raised to power 5 divided by 5 minus up to infinity. Tan hyperbolic inverse x equals to x plus x cube divided by 3 plus x raised to power 5 divided by 5 plus up to infinity. And this also equals to 1 by 2 log 1 plus x divided by 1 minus x. Now argument of z we can write here as argument of x plus iota y, which is equals to tan inverse y by x, and theta is equals to tan inverse y by x. Here for principal argument we use this. If the x and y in the first quadrant, then theta is equals to alpha. This is for principal argument. This is argument and this is for principal argument. And if theta is second quadrant, we used here theta is equals to alpha plus pi. And for third quadrant we use here theta equals to alpha minus pi. And for fourth quadrant we use theta equals to minus alpha. Here argument of z raised to power n equals to n argument z. Here some principal value of argument. Argument of z1 z2 is equals to argument of z1 plus argument of z2 plus 2 pi n plus. Here argument of z1 divided by z2 is equals to argument z1 minus argument of z2 plus 2 pi n minus. Here argument of z raised to power n is equals to n argument z plus 2 pi n and n. As we already discussed Cauchy-Riemann equation in previous video, now Cauchy-Riemann equation in polar form. Del u over del r equals to 1 by r del v over del theta, and del u over del theta is equals to minus r del v over del r. Now Cauchy-Riemann equation for derivative of w in polar form. Here w is equals to u plus iota v. So we can write here del w over del x equals to del u over del x plus iota del v over del x. Here if we differentiate w in term of z, we get cos theta plus iota sin theta del w over del r. Here if we differentiate del w over del z, we also get this value del w over del theta. There are two forms of del w over del z. Now another theorem, if f of z equals to u plus iota v and is an analytic function in domain D, then the curve u, which is constant, and v also constant, are orthogonal families. Orthogonal families. For calculating their slope of tangent, du is equals to del u over del x dx plus del u over del y dy equals to 0. Now slope m equals to dy over dx equals to minus ux divided by uy if the two curves are orthogonal and if two tangents are perpendicular, then m1 into m2 is equals to minus 1 for two curves are orthogonal if two tangents here are perpendicular. Here minus ux divided by uy minus vx divided by vy equals to v by vx into minus vx divided by vy. This minus, so this equals to minus 1 using here Cauchy Riemann equation. Here this is ux is equals to del u over del x and vx is equals to del v over del x and uh, del u over del y, uy is equals to del u over del y, and similarly vy is equals to del v over del y. Here we use here Cauchy Riemann equation, which state that del u over del s is equals to minus del v over del x, sorry, del v over del y, and del u over del y equals to del v over del x. Sorry, this is plus and this is minus. Now another theorem. In this theorem we discuss about harmonic function and Laplace equation if fz is equals to u plus iota v and is analytic function, then u and v both are harmonic function. Any function which satisfy the Laplacian equation is known as harmonic function. This is Laplacian equation or if both u and v satisfy, then we can called u and v are harmonic function. If both u and v are harmonic function, such function u and v are called conjugate harmonic function. if u plus iota v is also analytic function, it is possible u and v are harmonic function, but u and v are not conjugate. If this condition is satisfied by u and v, then they are called harmonic function. But if del u over del x does not equals to del v over del y, does not satisfy Cauchy-Riemann equation, and del u over del y does not equals to minus del v over del x, then u and v are not harmonic conjugate. Let's do construction of an analytic function. If u is given, problem is we need to find v, and given that u plus iota v is analytic. For example, if u is given as this value and we need to find v, so we used here Cauchy-Riemann condition. First we find partial differentiation of with respect to x, and which will equals to derivative, partial differentiation of v with respect to y, and similarly for uy minus 2y, which is equals to minus of vx, partial differentiation of v with respect to x, and then integrate this value, we get value of v. Here vy is equals to 2x, on integration we get plus alpha x, where alpha x is some constant. Now integrate vx equals to 2y, we get v is equals to 2xy plus alpha dash x, where these also constant, and putting here alpha is equals to 0, so we get v is equals to 2xy. So f of z becomes u plus iota v, which is equals to this, plus iota 2xy. Now another method for construct analytic function, which is Milne's method to find f of z. For constructing analytic function without finding v, if u is given, and if v is given without using u and u is not given, for this case, as we know that fz is equals to u plus iota v. Here if z is equals to x plus iota y and their complex conjugate is equals to this, we can find the value of x and y in term of z and y. So we can write here u of z plus z bar divided by 2 comma z minus z bar divided by 2 plus iota v z plus z bar divided by 2 comma z minus z bar divided by 2. If u is given, this is case 1. Now f of z is equals to u plus iota v. If we find derivative of f dash z with respect to x, so we can write here this. Similarly, you can do with respect to y also. F dash z is equals to del u over del x. We can use here Cauchy Riemann equation. Del v over del x is equals to minus del u over del y. Let ux is equals to phi 1 x comma y, and uy is equals to phi 2 x comma y. For constructing analytic function, we used here f dash z is equals to phi 1 minus phi 1 x y minus iota phi 2 x comma y. Or for finding fz value, we used here putting x equals to z and y equals to 0. So this become this, and then integrate this term. We find the value of fz. Plus c. If v is given, similarly we used here f dash z is equals to del u over del x plus iota del v over del x, and we can use here del u over del x is equals to del v over del y plus iota del v over del x. And let's say this is psi 1 function of xy plus psi 2 function of x comma y. Here psi 1 is this value and psi 2 this value, and iota also is there. So now we can integrate both sides, we get the value of fz. And also here we put here x equals to z and y equals to 0. Let's do question on this topic. U is given, we need to find the value of v. Here first of all we need to find del u over del x, which is equal, we can write ux. So or we can write here 2x plus minus x square minus y square divided by x square plus y square whole square. As we know that f of z is equals to x plus z is equals to x plus iota y, and their complex conjugate is equals to this. And if we take their this value, this equals to this, as we know that. So this equals to this. equals to 2x. Sorry, this is not done by this method. Putting here x equals to z and y equals to 0 as we do in milne method. So u of x at z comma 0 equals to 2z minus z square divided by z square whole square, and this term is cancelled out by this, so we can write here this. Now this is ux at z comma 0. Similarly we can find here uy, which is equals to minus 2y plus now putting here x equals to z and y equals to 0, so u y z comma 0 equals to 0. Now f of x equals to integral, here this is the value of ux, so we write here uy value is equals to 0. So now integrating this term and comes to this plus c. Let's take c is equals to 0. Now f of x is equals to, as we know that z is equals to x plus iota y and their square is equals to divide by x plus iota y. Rationalize this term. Now squaring this, we get here x square minus y square plus, and solving this term we get here x divided by minus 2 iota xy plus x minus iota y divided by x square minus y square plus square. Now separating real parts and imaginary part. Here this is plus minus y by x square plus y square. Here we can compare f of x is equals to u plus iota v. Now comparing this equation we get v is equals to 2x minus y by x square plus y square. Let's do another question. In this question we need to prove u is harmonic. And given that u plus iota v is analytic. So u of x is equals to 2 1 minus y. If we find here this is del 2 u over del x square, which is equals to 0, as you can hear. And similarly uy is equals to minus 2x. And similarly, if we find double partial derivative of y, which is equals to 0, and if we can write this here, this is the condition of harmonic. Let's do a question on w is equals to log z. Here in this question we need to find the value of dw over dz. As we know, for Cauchy Riemann integral we can write this into this. So first of all we need to find the value of u and v. Here w is equals to log z, or we can write here z is equals to x plus iota y, and we can write here this r cos theta plus iota r sin theta. As we know that z is also equals to e raised to power iota theta, and also we can write here this. So we can write here this r raised to power r into e raised to power iota theta, or we can write here log r plus log e raised to power iota theta, or we can write here iota theta. Here, as we know that for complex number r is equals to root of x square plus y square, so we can write here this value plus here this is theta. For complex number, as we know that theta is equals to tan inverse y by x, so we can write here tan inverse y by x. Now we can see this is real part and this is imaginary part, so we can write here u is equals to log root x square plus y square plus iota tan inverse y by x. Let's find the value of del u over del x. On differentiation, partial differentiation, we get this value, and del u over del y we get this value. Now del v over del x is equals to this, which is equals to minus y divided by x square plus y square. Now del v over del y is equals to y square divided by x square plus 1 into this. Now here you clearly see that del u over del x is equals to del v over del y, and del v over del x is equals to minus del u over del y. So we can write here dw over dz is equals to del u over del x plus iota del v over del x. So we can write here del u over del x value, which is equals to x divided by x square plus y square plus iota del v over del x is equals to minus y divided by x square plus y square. So we can write here this value, or we can write this value as like this value, and this is cancelled out by this term, and this is equals to z. So the answer is 1 by z. Let's do another question. In this question, the value of u and v is given, and finding in this question we need to prove this is a harmonic function and u and v are not harmonic conjugate. To prove u and v are harmonic function, and also prove u and v are not harmonic conjugate. Here first of all we need to find the value of del u over del x, which is equals to 2x, and del 2 u over del x square is equals to 2, and del u over del y is equals to minus 2y, and del 2 u over del y square is equals to minus 2. If we write here del u over del x is x square plus del u over del y square equals to 0. Now finding del v over del x. Minus 2xy divided by x plus y, x square y square whole square. And now finding del 2v over del x square, which equals to this value. Now finding del v over del y, which is equals to now finding double partial differentiation of del v over del y square, del v over del y, which is equals to this. As you can see, if we add these both terms, we get 0. Hence, both u and v satisfy Laplace equation. So, u and v are harmonic function. But as you can see, ux does not equals to vy, and uy does not equals to minus of vx. Now Milne Thomson method, case third. When u minus v is given, then f of z is equals to u plus iota v, and multiply both sides by iota, we get this value. This is first equation and this is second. Adding first and second equation, we get this value. Now you can see that this is capital U plus and this is capital V, and this capital U plus iota V is equals to capital FZ. So we can write here FZ is equals to F capital Z divided by 1 plus iota Z. 1 plus iota. Similarly, we used in this case for finding the value of Fz as we used in case 1 and case 2. Now, if case 4, if U plus V is given, then Fz is equals to U plus iota V, and multiply both sides by iota. We can write here this, and similarly add this equation. We can write this value again, and similarly capital Fz is equals to U plus iota V. This term is capital U and this term is capital V. So we can write here F capital Z is equals to 1 plus iota small fz. Here V is equals to U plus V is given for in this case. So we can find value of Fz is equals to capital F of Z divided by 1 plus iota V. Let's do question on these two cases. Question 1, U minus V is equals to U minus V is equals to, so small u minus V is equals to x minus y into x square plus 4x plus y square, and f of z is equals to u plus iota v and is an analytic function, and z is equals to x plus iota y. We need to find fz. So using this third and fourth case, in this question you can see this is given u minus v, so we use here third case of Milne Thomson method. So we can write here this, and this is capital U and this is capital V. So capital Fz is equals to U plus IV, and here you can see that U minus V is given, so we write here capital U, which is equals to this. Now we do here similar step as we used for case 1 and case 2, but in this case we used here for case 1 as is capital U is here, so del U over del x is equals to this value. On differentiation we get this value, and similarly we let this value is phi 1, and similarly we put here x equals to z and y equals to 0. So phi 1 z comma 0 equals to 3z square. Now finding del u over del y equals to this value. Now similarly we find also here phi 2 z comma 0, so we get this value. Now if we now finding the value of capital Fz u plus iota v, and if we find this, which is equals to this, here we have only u value, so using here Cauchy Riemann condition we can write here this, and equals to phi 1 z comma 0 minus iota phi 2 z comma 0, and we get here 3z square minus iota 3z square. Now f of f dash z equals to this value. Now integrate, so we get capital Fz, which is equals to z cube minus iota z cube, or we can take common, also plus c constants come, and we can take here common z cube, and comes this value. Now this is the value of capital Fz. Now put this value in this condition. Here 1 plus iota small fz equals to capital Fz. So small fz is equals to divide by 1 plus iota, and c divide by 1 plus iota, or we can write this term c1, and rationalizing this term on solving we get here this value. Now let's do another topic, which is complex integration. Line integral. A line integral along a curve is defined as we know that, for normally if we have a function fx is given, for in complex number we used here fz dz. Along a curve, here this is a curve from a to b, here f of z is equals to u plus iota v, and z is equals to x plus iota y. Now integration of f of z dz for closed curve is equals to this value, or we can write this value as this u dx minus v dy. This is the real part plus iota integration v dx plus u dy, and this is the imaginary part. Now for doing complex integration, first of all we need to understand what is simply connected region. A connected region is said to be simply connected if all the interior point of a closed curve drawn in a region are the point of the region. Now another another condition is multi-connected region. It is bounded by more than one curve. For multi-connected region, the curve is bounded by point is bounded by more than one curve. We can convert a multi-connected region into a simply connected region, one by giving it one or more cuts. Here you can see This is simply connected region. This is C1 and this is C2. This is simply connected region. And this is multi-connected region. This is curve C1 and this is C2. Here this is curve C3 and this is curve C4 and this is curve C5. Now this is simply connected region. As we convert this from multi-connected region. This is C2 and this is C1. Now mesomorphic region. For a region R, if the function is analytic in the region R, expect at a finite number of poles. Now single valued function has only one value. For example, f of z is equals to z square, and another is multi-valued function, more than one value. Here f of z is equals to z raised to power 1 by 2. Now another point is multi-point of arc. Multi-point of arc. If an equation is satisfied by more than one value of variable in the given range, then it is considered as multi-point of arc. Jordan arc. It is a continuous arc without points. Some after we will do some question on Jordan arc. Now regular arc. If the derivative of the given function also continuous in the range, then the arc is called regular arc. Now contour. It is a Jordan curve consisting of continuous chain of finite number of regular arcs. Now another zero of an analytic function. Value of z which the analytic function fz becomes 0 is said to be zeros of z. For example, this is equation and having zeros z equals to 1 and z equals to 2. Now another important theorem, which is Cauchy integral theorem. for a function fz which is analytic, and it f dash z derivative continuous at all point inside the curve c, sorry, inside a simple closed curve, let's say, which is c, then f of z dz equals to 0. Let's do a question on the Cauchy integral theorem. Integral 3z square plus 7z plus 1 divided by z plus 1 dz. Here mod of z is equals to 1 by 2. Here C is a circle is given. So first of all we need to find poles. For finding poles we put the denominator values equals to 0. Z plus 1 equals to 0. So you can see here z equals to minus 1. And their order of pole is 1. As you see here, mod of z is equals to 1 by 2 given. So using this condition, we can see that the circle is start from center at O 0 and radius is given as 1 by 2. So the diagram become this. This is 1 by 2. Here you can see z is equals to minus 1. If we see in this diagram, z equals to minus 1 does not lie inside inside this figure. So this integral become equals to 0, as we used here Cauchy integral theorem. Let's do another question. This is given condition. Here we need to find the poles. So we put this equation equals to 0. And using here this formula, here z is equals to this value. Here you can see order of pole is equals to 1, and there are two poles, minus 1 plus 2 iota and minus 1 minus 2 iota. Let's plot this point on this xy axis. Here you can see center is at 1 minus 1. So this is minus 1 and radius is given as 1. So the diagram become this. This is minus 2. Now as you see here, now plotting this point minus 1 and plus 2 for y-axis, and this point is outside the circle. So for this integral is 0, and similarly for minus 1 and minus 2 iota. So this minus 2 iota may be here. So these both points are outside the curve. So the integral is equals to 0. Now extension of Cauchy's theorem to multiple connected region. If fz is analytic in region R between two simple curves, then we can write this integral fz dz for closed curve 1 equals to integral fz dz for closed curve C2. Now Cauchy integral formula: f of a is equals to 1 by 2 pi iota integral fz divided by z minus a dz. Now for this represent differentiation, so this equals to this n factorial divided by 2 pi iota integral fz dz divided by z minus a whole power n plus 1. Now another important theorem, morera's theorem, and this is converge of Cauchy integral theorem. If fz is continuous function in a domain D, and if every closed contour C in the domain D, then integral fz dz equals to 0. Then function fz is analytic within D. Now most important topic in Cauchy integral theorem, which is Cauchy's inequality. If fz is analytic within a circle, that is mod of z minus a equals to r, and if mod of fz is less than equals to m on circle C, then mod of f raised to power n, sorry, this is the nth power derivative, mn factorial divided by r raised to power n. Let's prove this. Here given, you can see f raised to power n is equals to n factorial 2 pi I. Here we used here Cauchy integral formula. Now this value may be greater equals to 0 if we put here fz equals to m. So we can write here factorial n divided by 2 pi iota m divided by r raised to power n plus 1 integral 0 to 2 pi r theta d theta. Here mod of z minus a is equals to r. So we used here, this become r raised to power n plus 1. And since as we know that z is equals to r raised to power, oh sorry, r into e raised to power iota theta, and if we write here dz equals to, which is equals to this, if we take here mod, and here this term is z, so we can write here what, so this equals to r d theta. Here a plus iota b is equals to mod of a plus iota b is equals to root of this value as we know, which is equals to a square plus b square. Then if we find the modulus of this value, we can write this value, and this equals to r. So putting this value in this formula, we get this, and after integration this value you can write m by r raised to power n plus 1 2 pi r, and this 2 pi is cancelled out by this, and this r is cancelled out by this, so this equals to m n factorial divided by rn. Hence proved.